To analyze a structure, we take the reality, which is complicated, and turn it into an idealization that reasonably represents the real situation. In order to create reasonable idealizations of loads, we need to know how they act on a structure. Dead load acts downward because it is a gravity load, and it acts along the length of the member. Think about it. No matter what shape the member is, the self-weight acts along its full length. So idealized dead load looks like this. Live load can act everywhere, in just some locations, or not at all. The chairs in this room are fixed to the floor, so they would be dead load. However, the people who sit on them are considered live load. This is a great example of the possibility of live load acting nowhere, because at the time I took the photo, there was no one else in the room. Live load also acts downward because it is a gravity load, but it acts along the horizontal projection of the member. Think about it. No matter how steep I make the floor in this room, I can't put in more rows of seats. Each row needs a set horizontal distance for the walkway and for the seats. So, on an inclined member, the net force due to live load is based on the horizontal length of the member instead of the overall length like we use for dead load. Snow load is another gravity load. It acts downward. The amount of snow that falls from the sky does not change based on the structure below it. So no matter what the incline of the structure, the weight of snow that falls is based on the horizontal dimension of the structure, not its overall length. The codes start with the ground snow load, the weight of snow that falls from the sky onto flat ground. That amount can then be modified for conditions like steep roofs, which would tend to have some snow slide off. If a roof has vertical components, wind can move snow from parts of the roof and gather the snow next to the vertical face. We call that drifting. The codes cover how to anticipate the different distributed load magnitudes for drifting as well, but the load is always on the horizontal projection. Wind is not a gravity load because it is not based on gravity pulling down on the air particles. Wind load is caused by the air particles colliding with the structure. Therefore, wind load acts normal to the structure along its full length. The effect of wind can be pressure or suction. Where the air particles are colliding with the structure, we have pressure. You can see the effect in this photo. The wind is blowing from the left to the right. As the wind hits the left side tarp, the wind pushes onto the tarp, causing pressure. On the other side, the diverted wind causes suction, so the wind is pulling outward on the tarp. On both sides, the pressure is normal to the surface of the tarp. Some structures must support significant fluid or soil. Those loads are hydrostatic, so they increase with depth. Because they are hydrostatic, they act normal to the surface. So for an inclined surface, the distributed load would be triangular or trapezoidal. Fluids, like water or granule materials like grain, tend to cause triangular load. If there is a surcharge weight acting on soil, the soil pressure on the structure won't be zero at the surface, so we get a trapezoidal distributed load. Earthquake loads are different from all the others we have discussed. For all the others, the load acts on the structure. During an earthquake, the ground moves under the structure. To see the effect, consider what happens when an earthquake moves the ground under this structure to the left. The inertial mass of the structure initially keeps the rest of the structure basically where it was. The energy stored in the curved members then starts the structure moving left. This sketch shows the motivation for one way we idealize earthquake load, an equivalent static load. To put the structure in this shape, we would need lateral load acting at each level. In reality, this is a dynamic process, but the codes help us calculate an equivalent static force. Earthquakes, also called seismic events, are essentially waves passing through the soil. Those waves have horizontal and vertical motion. Sideways movement dominates, but vertical movement can still be significant. If we consider the vertical movement of a wave, at some point the ground moves down. Again, the inertial mass initially stays where it is, so the columns must get longer. The equivalent static force in this case is upward distributed load at each level. As the wave passes and the ground moves up, the equivalent static force would act downward. As I mentioned in the last video, calculating the magnitudes of each of these forces is outside the scope of what we have time to cover. What we want to focus on is how the load acts on the structure once the magnitude is calculated.